Hello viewers, in this session I'm going to talk about the partial derivatives. So previously we have looked at how to find the derivative of a function of a single variable. We would like a function, say y is a function of x. In this case, the function y or the variable y depends on only one variable, which is x. So when we find the rate at which y changes per unit change in x, we call that the derivative of y with respect to x. In this case, there is only one independent variable. But in many cases, especially in practical situations, the variable y may depend on more than one variable. So we want to look at the case where the function depends on more than one variable. Then we'll see how we can differentiate this function. So by the end of this session, we should be able to find the first order and the second order partial derivatives, and also the total derivatives of functions of more than one independent variable. Later we shall look at how to find the stationary points for functions of two variables. So, as we have said, previously we explored how to find the rate of change of a function with respect to a single independent variable, and we learned how about the slope of a tangent line, the derivative as a function, and its application to find the optimum values, which are the minimum, maximum, and inflection points. However, in real-world systems and applications, functions usually depend on more than one independent variable. And this is where the concept of partial derivatives becomes essential. Imagine you are analyzing the market demand for certain products in economics, for example. In a simplistic scenario, you might have a function that describes the demand of a product based on its price alone. So this function, this is a function of a single variable, and finding its derivatives gives you some variable information about how demand changes with respect to the price of that commodity. But let's consider a more realistic scenario. The demand of a product may not only depend on its price, but also on other factors such as the consumer income, the price of substitute goods, because you say when the price of a commodity goes up, for example, if you consider cooking oil, for instance, if 1 blood of a cooking oil goes up, consumers may tend to buy or purchase other brands whose prices have not changed. So the price of consumer product of substitute products will affect the demand of this particular products, not just the price alone. The income of consumers. If people are earning more, they may tend to consume some certain products, but if they earn less, then they may tend to change what they are consuming. Also, another important aspect or factor that may affect the demand of a product is the advertising expenditure. Because if you don't advertise your products, people are likely not to know about them, and therefore they may not buy. In this case, the more money you spend on advertising, then that may have an effect of increasing the sales. So in this case, our function representing the demand becomes a function of more than one variable, what we shall call a function of multiple variables. For example, in the above case, let's denote the demand of a product by day, and this depends on the price P, but also on the consumer income I, prices of substitute goods S, and the advertising expenditure A. So mathematically, we write this as D is equals to f in bracket p comma I comma s comma a. This means that p, I, s, and a are independent variables, all affecting the demand D of the product. So in this case, f is the demand function. So now, when we talk about partial derivatives, we are interested in understanding how this demand function will change per unit change in each of the independent variable while keeping others constant. For example, we ask, what happens to the demand if we increase the price of this commodity while keeping the income of consumers, prices of substitute goods, and the advertising expenditure constant? Suppose we change only the price of this commodity while all the other variables are kept constant. What will happen to the demand? So this is the concept of partial derivatives, and this is what we want to explore in this section. So in general, if z is a function that depends on two independent variables, x and y, then we shall write in notations that z is equals to f of x comma y, to mean that x and y are independent variables. So to differentiate z with respect to x, we shall assume that y remains a constant at that particular instant when x is changing. So this derivative shall be called the first order partial derivative of z with respect to x. Sometimes we denote this by dz dx. Then we put the square brackets there and write y. This quantity that we write here is the variable that we assume that will remain constant when we are differentiating z with respect to x. But a better notation, we write this. We use the carry d to mean the partial derivative of z with respect to x. In this case, we assume that even if z is a function of more than one variable, only x is changing at this particular instant. So similarly, for this function which depends on x and y, we can differentiate z partially with respect to y by assuming that x remains a constant at the instant when y is changing. And this derivative, we shall call it the first order partial derivative of z with respect to y. So we write dz by dy, then we put the brackets like that, then we put x here, meaning that x remains constant at the instant when y is changing. But a better notation, we use the carry d, the partial differential operator. So we call this the partial differential operator. So when we write z here, meaning that we are differentiating z partially with respect to y. Let's do an example. We want to find the first order partial derivative given the function here. So we note that in this case, z is defined as a function of two variables which are x and y, and therefore we differentiate z partially with respect to x, and also we can differentiate z partially with respect to y. In this case, we find the two first order partial derivatives. So to find the partial derivative of z with respect to y, or with respect to x, we shall assume that y is a constant. So when we are differentiating a term like this, a term like the first one now, the partial derivative with respect to x of x cubed y squared, we shall treat y as a constant and therefore write y squared, then differentiate with respect to x the quantity x cubed. So when we differentiate x cubed, then we shall get we shall get 3x squared. So that 3x squared is then multiplied by what we have assumed to be a constant, which is y squared, to get 3x squared, y squared, which is the first term here. If we go to the next term, this term, when we differentiate 4x squared, we just get 8x. But going to the next term, y cubed, remember we are assuming that y is a constant. So the derivative of a constant is 0. So when we differentiate y cubed with respect to x, we get 0. And of course, 7 is a constant, so the derivative of 7 is also 0. So in this case, we get 3x squared y squared plus 8x. Now, similarly, to differentiate this function partially with respect to y, then we shall assume that x is a constant. We assume that x is a constant, so that we treat x now as a constant, and we differentiate the terms, each term there, with respect to y. So when we take the first term, for example, which was x cubed y squared, that was the first term, and we want to differentiate this partially with respect to y, then we shall write, because x is to be treated as a constant, then we push it forward, x cubed, then we write the partial derivative with respect to y of y squared. Now differentiating y squared will give us 2y. Then when we open the brackets here, we get 2x cubed y. That is the derivative of the first term there. If you go to the next term, which is 4x squared, remember we are treating x as a constant. So when we differentiate a constant, we get 0. So the derivative of the second term will give us 0. When we go to the third term, which is minus y cubed, we are differentiating y cubed with respect to y. So we get minus 3y squared, which is that second term there. Then the last term is a constant, so the derivative is 0. So in this case, the partial derivative of z with respect to y is 2x cubed y minus 3y squared. We have a second example here, and we can work out the same way. We have z is equals to 4x cubed y raised to power 4 minus 5xy cubed minus plus x squared minus 7y squared plus 9. So when we want to find the partial derivative of z with respect to x, we differentiate each term with respect to x, assuming that y is a constant. So if you look at the first term, there is a constant 4, and there is another constant y raised to power 4. So we shall write 4y raised to power 4. Then the derivative with respect to x of x cubed. The second term we shall write minus 5y cubed. Then the derivative with respect to x of x. The next term we have the derivative with respect to x of x squared. And then the last two terms, because they do not contain x, then those ones will be treated as constant. So I can write minus 7y squared plus 9. Remember, the derivative of a constant is 0. So when we differentiate x cubed here, the first term, we get 3x squared. So 3x squared multiplying 4y raised to the power of 4 will give us 12x squared y raised to the power of 4. And in the second term, when we differentiate x power 1 with respect to x, we get 1. So 1 multiply minus 5y cubed will give us minus 5y raised to the power of 3. Then the next term, when we differentiate 2x x squared, we get 2x. Then the last two terms, when we differentiate, because this y is treated as a constant here, 9 is also a constant. Differentiating a constant will give us 0. So the partial derivative of z with respect to x will give us that. And similarly, when we want to differentiate this partial with respect to y, now we shall be assuming that x is a constant. So in the first term, we shall treat this as a constant, the whole of that. Then we differentiate y raised to power 4. When we differentiate y raised to power 4 with respect to y, we get 4y cubed. So 4y cubed multiplying 4x cubed will give us 16x cubed, y cubed, which is the first term here. The next term, we treat the whole of this as a constant, then differentiate y cubed with respect to y. So that will give us 3y squared multiplying minus 5x, giving us minus 15xy squared. The next term does not contain y, meaning that that's a constant term as far as this derivative is concerned, and the derivative is 0. Then the next term here, minus 7y squared, we differentiate with respect to y, we get minus 14y. The last term, 9, is a constant, so the derivative of a constant is 0. So basically, that is how we find the partial derivatives. Notice that the rules of differentiation remains valid. The rules of differentiation remains valid. The only difference is that there is an assumption we are taking. When we want to differentiate the function partially with respect to x, we assume that y is a constant. And when we want to differentiate the function partially with respect to x, then we assume, when we want to differentiate the function partially with respect to y, then we assume that x is a constant. So the rules of differentiation remains valid, the same rules. Now, next we want to look at the second order partial derivatives. And I want us to take an example so that we can understand this well. So we consider a function z, which is given as x cubed y raised to power 4 minus 4xy squared. Then we want to differentiate this partially with respect to x and partially with respect to y. So notice that when we differentiate partially with respect to x, we assume that y is a constant. So the first term will differentiate x cubed, then multiply by y raised to power 4, which will give us 3x squared multiplied by y raised to power 4. The second term, we have 4y squared. Then we differentiate x, which will give us 1. So that the derivative is 3x squared y raised to power 4 minus 4y squared. This is the first order partial derivative of z with respect to x. Similarly, when we want to differentiate z partially with respect to y, then we assume that x is a constant. So the first term we differentiate y raised to power 4, which will give us 4y cubed. We multiply by x cubed to get 4x cubed y cubed. The second term we differentiate y squared, which will give us 2y, and 2y is multiplied by 4x. This will give us 8y. There is the sign is negative here, so we carry the sign. So these are two first order partial derivatives. These are function of two variables, x and y, meaning that there exist two first order partial derivatives. The first order partial derivative of z with respect to x, and the first order partial derivative of z with respect to y. Now, from these results, we note that each of the first order partial derivative obtained here is also a function of two variables, x and y. So we see the first derivative depends on both x and y, the second partial derivative is also a function of two variables, x and y. So it follows, therefore, that each of these derivatives can be differentiated with respect to the two variable quantities, x and y. And this should yield a total of 4 second-order partial derivatives. So we can take the first partial derivative, which is this one. This is a derivative of z partially with respect to x. Then we differentiate that partially with respect to x. So we are taking the partial derivative of z with respect to x, which we had obtained as 3x squared y raised to power 4 minus 4y squared. So we can differentiate this partially with respect to x. So when we differentiate partially with respect to x, here, notice that we take the same assumption that y is a constant. So the term that does not contain x will be a constant term, and therefore, when we differentiate, we get 0. The first term contains x, so we have x squared. So when we differentiate with respect to x, we get 2x times 3 times y raised to power 4, which will give us 6x y raised to power 4. So this is a second order partial derivative. Notice that this one is obtained by first differentiating z partially with respect to x here, and then again partially with respect to x. But we could take the same function, partial derivative of z with respect to x, and this time differentiate partially with respect to y. In this case, we shall assume that x is a constant because we are differentiating partially with respect to y. So when we do that, we get the second order partial derivative. And notice that this one is different from the first one because this one is obtained partially with respect to x and also partially with respect to x. So here we are differentiating, in the first case, we are differentiating the function z twice, partially with respect to x. But in the second case, we differentiate z partially with respect to x, then z partially with respect to y, meaning that we call this the second order partial derivatives, a mixed second order partial derivatives, because we have the differentiation with respect to x and also the differentiation with respect to y. Now, when we take the other function, the partial derivative of z with respect to y, we can do the same. We can differentiate this partially with respect to x, and we can also differentiate the same partially with respect to y. When differentiating partially with respect to x, we shall assume that y is a constant. When differentiating partially with respect to y, we assume that x is a constant. So in this case, when we differentiate partially with respect to x, we are differentiating these terms partially with respect to x, we get 12x squared y cubed minus 8y. But when we differentiate partially with respect to y, here, notice that here, because we are differentiating partially with respect to y, we differentiate y cubed to get 3y squared. We differentiate y here to get 1, so we get minus 8x times 1. So these are the 4 second order partial derivatives. We have this one, we have this, and this. So for a function of two variables, there exist 2 first order partial derivatives and a total of 4 second order partial derivatives. So from this analysis, it is noted that there exist 4 second order partial derivatives. This is d squared z by dx squared, d squared z by dy squared, d squared z by dy dx, d squared z by dx dy. These are 4 second order partial derivatives. The last two, however, if the function z is continuous, these two are always equal. As you can see here, these two are equal. So normally it doesn't matter whether, for a continuous function, it doesn't matter whether you start differentiating z with respect to x, then followed by differentiation with respect to y, or you differentiate partially with respect to y first, followed by differentiation with respect to x. This will give us the same results. So in total, we say there, for a continuous function of two variables, there exist three different second-order partial derivatives. These are d squared z by dx squared, d squared z by dy squared, and d squared z by dx dy, or d squared z by dy dx. Once you find only one of these, you don't have to find both, because they will be equal provided that the function z is continuous. Now we have an example here. We have a function of two variables x and y defined by z is equals to x cubed y squared plus 2xy cubed minus x raised to power 4. The problem is to find this first or the second order partial derivatives. So as usual, we start by finding the first order partial derivatives. So we differentiate z partially with respect to x, the derivative of z partially with respect to x, which will give us 3x squared y squared plus 2. Remember, the second term, we only assume that the variable is x here. So x, the derivative of x power 1 is 1. That will give us 2y cubed, then minus 4x cubed. This is the first order partial derivative of z with respect to x. Similarly, we can differentiate z partially with respect to y. This time we assume that x is a constant. So when we come to the first term, for example, we differentiate this to get 2y. When we come to the second term, we differentiate y cubed to get 3y squared. But we multiply 2y with the constant here, which is x cubed. We multiply 3y here with 3y squared with the constant, which is 2x here, to get 6xy squared. The last term, because it does not contain y and x is assumed to be a constant, then the derivative is 0. So in this case, we get x cubed in the first term times 2y. In the second term, we get 2x times 3y squared, which will give us this. Now, we now take each of these first order partial derivative and differentiate again partially with respect to x and partially with respect to y. So if we take the first one, so you want to find the second order partial derivative of z with respect to x twice. So this is the same as the partial derivative with respect to x of 3x squared y squared plus 2y cubed minus 4x cubed. So the assumption is that x is the variable, y is a constant. So when we come to the first term here, we differentiate x squared to get 2x. So that will be 2x times 3y squared. The second term does not contain x, so the derivative is 0. Then the third term we get 12x squared. So in this case, we have 6xy squared minus 12x squared. This is the second order partial derivative, d squared z by dx squared. So similarly, we can take the same function, 3x squared y squared plus 2y squared minus 4x. That is the same function, which is the partial derivative of z with respect to x, which is 3x squared y squared minus, this is plus 2y squared minus 4x cubed. And now differentiate this partially with respect to y. So we find the derivative with respect to y of this function. So this will be the partial derivative with respect to y of 3x squared y squared plus 2y squared minus 4x cubed. So taking the first term, we differentiate partially with respect to y. So we are going to have 3x squared. The derivative of y squared is 2y. Then plus 2y, 2 times the derivative of y squared is again 2y. And then we have 0, the last term, because the last term does not contain y. So in this case, when we open the brackets, we get 6x squared y plus 4y. This is the second order partial derivative of z with respect to this mixed order derivative. The first derivative is a differentiation with respect to x, and then followed by the differentiation with respect to y. So this is a mixed order derivative in this case. 6x squared. Sorry, the second term was 2y cubed, not 2y squared. This was 2y cubed. So when we differentiate y cubed here, we get 3y squared, and not so 3 the derivative of y cubed is 3y squared. So 3 times 2 is 6y squared. Which is this. Now, we have said that the mixed order derivative, regardless of whether you differentiate with respect to x first, then followed by the differentiation with respect to y, or you do it the other way, you'll get the same thing. So we are not going to do the other one, because we have done this one. But when we come to the second order, the first order partial derivative of z with respect to y, then we differentiate this partially with respect to y. So in this case, we have 2x cubed y, and let me do it here. So the partial derivative of z with respect to y is equals to 2x cubed y plus, we have 6xy squared. So we can differentiate this partially with respect to y. This will give us the partial derivative with respect to y, 2x cubed y plus 6xy squared. So say that now, because we are differentiating partially with respect to y, then we treat x as a constant. So in the first term, we shall write 2x cubed, then differentiate y raised to power 1 with respect to y. And in the second term, we shall write 6x, then differentiate with respect to y squared. So the derivative of y raised to power 1 is 1, so we get 2x cubed as the first term there, then plus 6x times 2y, so that we get 2x cubed plus 12xy. This is the second order partial derivative of z with respect to y twice. So these are the three second order partial derivatives. These are the three second order partial derivatives. So when you want to find the second order partial derivatives, the first thing is to find the first order partial derivative. Then we will differentiate these functions again, partially with respect to x and also partially with respect to y. And we have said The rules of differentiation remain valid. The only difference is that there is an assumption that we are taking that when we want to differentiate the function partially with respect to x, we assume that y is a constant. That's the only difference with the other derivatives. But the rules of differentiation remains valid. So this is how we carry out the partial differentiation. And in this session, we're going to stop there. And in the next session, we shall look at the total derivatives. Thank you and have a blessed day.